Okay, so that was the first technical obstruction. And so now let's get started. I want to talk about search, and search is a very, very broad topic because search is basically everything that you do to limit your data set to get the results that you want. So what I'll focus on mostly is what we call unstructured search or full text search. And I'd like to show you how this actually works and what you can get out of it and why you should and sometimes shouldn't choose different tools for different jobs. So what is this search that we will actually be talking about? Like the end result looks something like this. It's an interface to data that you type something in, you have some other controls, and you get the results back presented in a clean and nice way that includes all the information that you're interested in. So not just the actual results, but also the number, sorted by best match. You can highlight the snippets that actually match within the documents or within the results. You can see the distribution across categories or whatever's relevant for that given data set. So it's all about basically that search is not just one input field, even though that's the most important part. It's just anything that you do to make your data available for users and make it presentable and above all discoverable. So how do you implement this? So the first native approach, if you have a bunch of books in your library and you want to see which one of them actually mention Django. So the first thing that you do, the first approach is you sit down and you read every single book you have in your library, and you just put aside all those that mention Django. In case it isn't books but files, you just do a grep-r I Django stop, which is essentially the same thing except the computer is doing the reading. So it's slightly better, but not actually that much. And the equivalent in Django world is just run a query set where you're looking in title and in body for something that contains Django, regardless of case. So again, slightly better than grep, but very same thing. And I strongly encourage you not to ever do this, ever, for several reasons. First, it just doesn't work. It might work with a keyword like Django, but if you're looking for a document about running or something like that, how do you know if you should search for run, or running, or runs? It just wouldn't match. Also, it wouldn't give you any sort of relevancy. It wouldn't say that this document matches well and this just barely. And finally, it will just absolutely kill your performance. It just doesn't scale at all. Because every single query, any one of these three approaches just don't scale. You're not going to read every book in your library every time you're looking for something. The same way you shouldn't force your database to read through your entire data set just because you're looking for something. So how do you actually solve this? Like this sounds like a problem that somebody must have had before, right? Like people have been around text and books for quite some time. So sure, there must be a better way. So in a monastery far, far away, around the year 1230, there was basically a first occurrence of an index in recorded history. It was called the Bible Concordance, and what it was an alphabetical list of biblical words with links to passages that in the Bible that actually contain these words. And this is exactly what we're looking for. This is a data structure, pretty old one at that will enable us to look up things very quickly. So we have a list of words, and it's alphabetical, so it's very effective for searching. So we just look up Django, and we immediately have the list of documents, a list of books, or Bible passages that actually mention Django. Guess how many there are. So this is a research that has been done for us quite some time ago, and we can adapt it to our modern age with computers and spaceships and stuff. Still don't like cars. So this is a structure that we call an inverted index, and this is how it would look actually in modern days. So here I have an index with just 5 terms: Django, Flask, Jazz, Python, and Web, and 4 documents, 4 files in this case. And this data structure will now allow me to query my data set, the 4 files, very effectively. So for example, if I want the documents that match Django and Python, I just take the 2 lists. I take the 2 posting lists, is the official term, and I merge them. So I walk the 2 lists, and whenever I see a common document, that's the result. So in this case, the result is file 2. And this is a very nice approach because first it's very effective because I'm just merging sorted lists. That's a very effective operation and also an operation that lends itself well to further optimization. And also it has some interesting characteristics. For example, it doesn't really matter if those 2 lists came from the same index, which means I can actually query different fields or even different data sets as long as the document IDs are in sync, which otherwise they probably wouldn't be called IDs. It will actually work. So this gives me immediately the option of querying across fields, across document types, across anything, and always just use an index. That's already something that a typical data store doesn't give you, because there needs to do difficult voodoo to figure out which index can I use, can I supplement it with any other. Now here I'm always using an index in a very efficient manner. And we will not stop there. So we have a very basic inverted index. Let's see what else can we do with it. So the first thing that you want to do when you're searching is, instead of and, you want to use or. That's super simple. You just merge the lists and take all of the documents that are in either of them. That's not very challenging. So for more challenge, let's take a phrase. So let's do a phrase search. For that, all we need to do is add a position to the posting list. So here we say that Python is, in the file 1, is on the 4th position. It's the 4th word in that document. In file 2, it's twice there. It's the 1st and 3rd word, and so on and so forth. So now, when I do a search for a phrase Python web, and I mark it that it's a phrase, I'm just merging 2 sorted lists. But now I will not be satisfied with just the same document ID. I also need the offset, the difference between the positions of the term Python and of the term web, to be exactly 1. And that will actually result in file 2, because you can see that Python is the 1st word in that document, and web is the 2nd word. So there actually is a phrase Python web. So again, something that would be fairly difficult to do in a traditional data store, we get almost for free. And you can immediately see that the offset doesn't necessarily have to be 1. We can say that the offset needs to be smaller than 3. For example, to allow for any arbitrary words that can come in between the phrase that we're looking for. For example, prepositions or articles or things that bear no meaning and the entire thing should still match, but it's not an exact match. So this gives us a lot of leeway in how we use things and what we can find. And just to reiterate over and over, we are again just merging sorted lists. Very efficient operation that can work across indices and fields, and it lends itself very nicely to optimizations. So now that we've seen a few things what we can do with an inverted index, let's see how we can get one, how we can build one. So as always, we start with the story. The story is that Django is a high-level, it's a very good story, but it's a text. It's some text that we can take and we'll build an inverted index from it. Which is a ridiculously simple thing. We just split it into words, and we find those words in the dictionary that we already have, or if they're not there, we'll add them there. and we'll add this document ID, to the posting list. That's it. That's all. But notice that I'm doing something more here. If you see the text and if you see the tokens, the terms that I get out of it, there are slight differences from the one that are pretty self-explanatory, like it's all lowercase. It's split by word. I've also omitted some words because I don't really care about the word is or a. Almost every text will have those, at least in English. So there's not much value in preserving those. I can just ignore them. In some cases, it might be problematic, and there are ways to solve it. For example, if you're running a music site and you need to search for the band The Who, then you need a different approach because this one will just not work. Also, there's a famous band, well, not really famous, but a band that I believe was founded just to give people that do search trouble. It's called The. It's impossible to find. So to avoid these situations that we would find every single document, we just get rid of those words. And we also normalize the words that we have. So normalization includes a couple of steps. And this entire process is called analysis, and it has several fairly well-defined steps. First, as with any parsing, we produce a stream of tokens, and then we act upon that token stream using something that we call filters. So the first filter would remove the spell words. The second one would lowercase everything. The third one would do stemming. So what stemming is finding the root of the word, the core of the word that makes the word have its meaning. So it will strip all the grammatical prefixes and suffixes and just keep the core of the word. And that can be a fairly complex process and fairly expensive. So there are some shortcuts. For example, if we look at the words that we have here, you can notice that some of that it's not really the core. There is more to be taken from that, and also some of these are not really words, like fragment. I mean, it's not a word, but it's something that was produced by something that we call an algorithmical scanner. It's a simile. It's a heuristics that employ a few very simple rules that work fairly well for English language to actually normalize words. So to produce a canonical representation of a word from any form. So from running, you get run. From developing, you get develop. So then when you do better, much better. Okay. So then when you actually search and you apply the same process for the query, you will actually get a match. So and the last filter that we applied in our example is synonyms. So you can see that instead of rapid, we have both rapid and fast. Those are synonyms, and rapid is it's a normal word, but not many people would think to search for it. But some people might be interested, what's the best framework for fast development? And there is no reason why they shouldn't still find Django, because Django is good for fast development, right? And just because it was written by a bunch of people with a lot of linguistic skills, that shouldn't prevent people to finding Django. So that's analysis. And the side effect of this process that I just described means that all of it, all the important parts in search, actually have an index type. So when you actually index the document, when you insert the document into the index, that's where the most important parts happen. It also means that if you change some of the rules, if you change the rules how you analyze stuff, you typically need to rebuild the index. So there is a downside to it, nothing is free. There is no thing like a free lunch. So that's one side effect. And the other side effect is we also need to apply this analysis to the queries. So if someone searches for rapid development or fast development in framework, we again need to find the development word and stem it into just the develop. Otherwise, it wouldn't match in the inverted index, and we wouldn't get our results. So, now we have our inverted index built. We can do queries, and we can get back the documents that match. But there's one critical part that we are still missing to implement the first piece of our search line, and that is relevancy. We need to know how well a document matches our query, how well a field matches the term. And again, this is something that there's been a lot of research in, and something where we can utilize the power of the inverted index. And more specifically, because the inverted index has all the terms from our entire data set, we know a lot of information about our data set. The most important part is we know the frequency and the occurrences of certain words. So we know which words are very common, and we know which words are fairly rare. And we can take that into account. And we can take that into account exactly this way. So this is a little scary, but don't worry, there's a human version on the next slide. But I just wanted to demonstrate that this is actually something that has a solid theory behind it, because there is a formula, so it must be solid and theoretical and everything. And it's also not that hard to understand. At the core of this formula is something that's called the TF-IDF weight, which basically just expresses that we care about how rare the term is, and how many times it's present in the document. So for each document, we calculate this value, which will tell us how common is this word compared to how many times it's present in this particular field. So if you have a word that's very common and you find it 10 times in the document, you say, okay. But if you have a field that's very rare, if you have a word, that's very rare, and you find it 2 times, and you know that it's only containing like 5 other documents, oh yeah, this is a good match. So to put it in a TLDR version, relevancy is based on the rarity of the term for that given index, which we have an index per field typically, and how many times it's there in that given field, in that given document. And also we take into account how long the field is. Because if we index the whole book as one field, and we find a term there 10 times, it's probably not that relevant. But if we find it 2 times in something that's a title, that's like 4 words long, that's very relevant. So again, an additional factor that plays into the relevance. And that's it. That's all we need to do a proper full-text solution. Now, when somebody presents us with an input type text field, we know what to do. We can go to our inverted index, which we've built using an analysis process, and we can look up all the documents that would match this. We even know how well it matches, and we can do some other operations. We can do phrase searches. If you are interested in something like a prefix match, that's very easy, because you have a sorted list of terms in the inverted index. So just find all of these that have the same prefix, and they'll be in a continuous block somewhere. So not that hard to find something that has the same prefix in a sorted list. Very easy. So we have the main part of the search interface covered. But even though it's the most important one, it still isn't enough, and we need more. But before we get to more, do we? No, it's probably better to do questions at the end. It's complicated with the microphone. Sorry about that. So let's keep developing. Let's keep developing. What's the next feature that we'll tackle is the highlight. So we need to actually highlight all the occurrences of the term in the results. And note that this might be a little difficult, because sometimes you would search for fast, and you would find something that doesn't even have the word fast in it. And that's a problem. So how do we do this? As with anything else, when in doubt, like take the inverted index and add some stuff into it. So currently we already have positions of the terms in the document. What we can add there is the exact offset in bytes. Like what was the origin of this word? So you can see that even though we had encouraged, the actual offsets is for the whole word encouraging. And rapid is without change, but we also see that fast has actually the same coordinates as rapid. So when we actually match on the fast term, it will actually highlight the rapid word. So again, just by adding some critical information to the inverted index, we enable additional functionality. In this case, we can highlight even things that aren't there. So that's another piece of the puzzle. Another piece to make our search more usable, more user-friendly, and generally awesomer. So moving on. The next part is a tad more complicated. It's the block on the left side that does filtering and faceting. And what faceting is basically an aggregation. It's an aggregation, and that's important for us because it gives us insight into the data. It gives us the distribution of the data across whatever buckets we define. For example, here we define buckets based on a language. So you can see that, not surprisingly, when I search for Django, the most common language is Python. Second one, JavaScript. I have no idea why it matches 105 Ruby projects, but why not? So you can immediately see at first glance, like, what's the distribution? And typically, if you click on one category like that, you will get the filtered results. So if you click on the Ruby word, you will get those 105 Ruby repositories. So it's the combination of faceting, which will give you the distribution, and filtering, which will then apply the filter that you wish. That will give you what in total we call a faceted navigation. And faceted navigation is awesome. And whenever I see a search that could have one and doesn't, I'm really, really sad, and I don't want to click it. And the reason is because this is a very powerful concept. It immediately gives you an idea. If you search for a hotel in San Francisco, you can do facets by price range, and you immediately see that you don't ever want to stay in a hotel in San Francisco. You don't have to sort, you don't have to go through all the hotels. You immediately see that the price range is from 500 to 600 and 10,000 to 5,000, even though that makes no sense. So you can immediately see that. You don't have to read. You can even visualize it very well. So here it's pretty hidden, so you probably cannot see it, but there's even like a colorful bar behind the languages that show you that visualize like what is the ratio. So it's very powerful. It gives you insight, and it allows you to filter and drill down very quickly. And it's very important when people don't know what they're looking for, which is pretty typical when they're searching. They really don't know what they're searching for, so this gives them options. Because otherwise, they just have to know what they're looking for. If I know that I'm looking for Django, I'm okay. But then I don't know what the options are. I don't know that I can filter by languages, and I don't even know which languages actually have something to do with Django. So how does this actually work? So the first piece is faceting. Faceting or aggregations basically has two parts. In the first part, take the result sets. And so all the documents that matched. And we divide them into buckets. And we can define the bucket in whatever way our imagination and our technology allows us to do. The typical one would be return value, which is exactly exactly what's happening here. We have a term for language, and for each language, for each value, we create a bucket. And then inside the buckets, we can define aggregations. The most simple one is just count. Give me the number of documents that actually fall into this bucket. Super simple, straightforward. But you can do more interesting stuff. You can maybe define sub-buckets, but typically you want to do aggregation on some other field. For example, give me the average price range, or give me the number of files in the repository, and give me an average or a standard deviation, or whatever aggregation you actually fancy. So it's not only popular for faceted navigation, but also for doing analytics. So this is a screenshot of Kibana, which we've already seen here a couple times, and it actually is powered entirely by faceting, because it defines buckets in the for example, with the timeline, it defines a bucket per time interval, and just has number of events as the aggregation, so count. And in the lower example, we have again a bucket per domain, per top-level domain. So per term, that's the terms facet. And you can see how you can actually use a search engine for something as obscure as data analytics. So very important again, and it again introduces the option of exploring your data, immediately seeing what's in the data without having to go document by document, line by line, and actually trying to build this picture in your head. So once we actually have all the values and we want to filter, that's where filtering comes in. So filtering is super simple. It uses the same data structure, the same inverted index as the queries, but with one exception. Typically, when you want to filter on something, you don't want to do analysis on it. The same goes for faceting, because I want to see Python. I don't want to see Python, which is what an analysis would likely make from the word Python. So for the stuff that I want to facet on, or filter by, or sort by, which we'll get to later, we typically want to turn off the analysis process and just put the verbatim value in the inverted index. And so that's one way filtering differs from querying. The other one, which is probably even more important, is it doesn't impact the score. It doesn't impact relevancy. Because it's either a 1 or a 0. So it doesn't, you cannot say that something is written in Python, but well, you can say that, but not in terms of the document. You cannot say that something is more Python than something else Python. That just makes no sense. Also, because of the implementation, filters are very fast and they are very cacheable. Especially in Lucene, which is one of the most popular engines for building inverted indices and everything like that. Filters are inherently super cacheable because they use a data structure called bitset, when they actually use a single bit to represent each document. And that's a data structure that's very efficient, obviously, and very, very cacheable. And also then working with these caches is super effective because you're essentially doing bit operations, which is pretty much the most effective operation that you can do on a CPU. So, filtering also perfect in combination with facets for faceted navigation. So now we've built our entire GitHub example. Everything that they have, we can now reproduce. We know how they did it. There's no secrets anymore. It's not magic. It's just engineering. But let's take it a step further. Let's see what else we can do. The first thing I want to show you how to do is the did you mean suggestions. So again, sometimes people don't know what they're looking for, or they're not sure how to spell it, or they make typos. There are even core committers that are known for making typos. So, what happens then? Typically, like when someone misspells Django and just search for Django, they're on the fly, like they cannot find it. But luckily for them, we actually have an inverted index. So we have a list of all the words that are in all our data sets. So what we can do is we can find the nearest words, nearest in terms of edit distance. So the number of operations, the number of typos you would have to make to go from one version to the other. The typical concrete metric that's used for this is called the Levenshtein distance, which is basically a number of atomic operations you have to make to a word to make it into another. So we can find all the most similar terms around this one. And if one of them is significantly more popular than the one that we search for example in this case, like Django probably isn't anywhere almost. But Django is a fairly popular word, right? Right? So the search engine immediately knows, hey, it's in all likelihood, this person just made a typo. Let's just search for Django instead and just inform him of that. So again, because we have all the information on the terms, we can suggest the closest terms that actually are in the data set. So again, something super simple. We can even do it based on phrases. So for example, my other favorite example is if you search for Johnny Walker, it's a little bit typical because Johnny in Johnny Walker is spelled with an IE, not with a Y at the end. So if you search for a phrase Johnny Walker with a Y at the end, you will not find the whiskey. And that's very surprising because both of the words individually are spelled correctly, but together they're not. But again, that's something that we can tell you and we can inform you that those two words, when they're together, they typically are in this form, spelled with IE. So very useful, especially for uninformed whiskey lovers. And I mean uninformed because they actually prefer Johnny Walker. So that's all of the theory that I want to present to you for now. And let's actually see some code. It's a Django conference, so it would be rude not to include Python or Django code, how you can actually use this. So now I will actually portray my origins because I actually work for Elasticsearch, so this examples will be based on Elasticsearch. But the principles that I describe are applicable across all the search engines. So first in Python, how do I actually search? So I import the Python client, I instantiate it, and I search. Done. It's literally that's easy. The queries are in JSON. So here you can see that I'm looking for something that contains Django in the title, and I want to do a facets per tag. So I want to do facets on tags and get the results. So on the top part, it's the raw example with the low-level client. The bottom example is using the not yet finished DSL library that I'm working on now that should provide you with a more approachable API. So you don't actually have to write JSON in Python, which isn't really nice. Okay, so this is how you search. If you want more, if you want to search across multiple fields and anything like that, it's just as easy as just changing this title or doing the exact code that you want. I don't actually believe that there is an abstraction that would be more useful than just a fancy DSL, so you don't have to write all the curly braces, because every search is different. You and you alone have expertise into how your data looks like and what you can do with it. So this is actually how to search. And the other example is, we are at the Django conference, so how do I integrate this with Django? How do I take my models and dump them into Elasticsearch? Fortunately enough, it also fits on the slide. So again, I just import a helper from the library that's used for bulk uploading. And then I just take the client, give it a terminal, in this case a generator that just calls to JSON on any model that it encounters, and it will just index it into an index that's called settings.esindex. And it will actually index it into a correct type based on the name of the model. That's all you need for the initial bulk loading. And then you have a function, sync to ES, that you just connect to all the relevant signals. So, post save. I cheated a little bit. There should be one more function that would actually handle deleted models. I leave that to your imagination. But this is, again, all you need to actually produce a functional search for your Django application. It's no magic. It's nothing but a few simple functions, one to do the bulk loading, and one to do the same. This is all the boilerplate. These two slides are all the boilerplate you need to implement the search. The rest, the stuff that's not on there, is specific for your application. You need to write that part. Nobody will write that part for you. So, how much time do we have? We have 10 minutes. So, before we get to some extra bits, which I prepared just in case, does anybody have any questions? I would like to hear your questions now. Yeah, so just come forward. Or just shout and I'll repeat the question.
We need the mic.
Oh, sorry.
How do you deal with other languages for the analysis?
Okay, good question. With other languages, you typically define a different analyzer based on what language it is. If you mix multiple languages, even inside a single document, what you can do, there's a trick. If we don't have enough questions, we can go over it, where you can actually apply multiple analyzers to a field and store it basically multiple times. So then when you do a search, you can say, let's just stick it all there and see what sticks. So you can search across all the different variants with the assumption that one of them will match, and if there is any chance. So that's one way. Another way is if you can define it for a document, so you can define it dynamically. So there is a field on the document that indicates which language it is, and the analysis process will take that field into account and choose a correct analyzer.
So basically it's built in.
Yes. Thank you.
The last time I used Elasticsearch, I had a small problem with highlighting. So you get this extra highlight field with all your data, but it misses the original data where no highlighting is. So basically you have the original fields and the highlighted fields. And in Django templates, it's not fun to move through the highlighting, see did I match this or not, and then decide what to display. Is there a shortcut or so I can take?
So there's no shortcut, because typically you don't want to display the whole text. You just want to display fragments. So that's why that is separately and shorter. If it's a short field, you can just ask Elasticsearch to highlight the entire thing and just use the things from the highlight. And unfortunately, you have to do a little bit of matching or something. Okay. Any other questions? You need to come over here.
Actually, something to add to the previous question. I had the same issue and chose to return whole source document with the results. You can just use the field research document. And one other question. I've got documents with a lot of data, but only a few fields or per language. So would be the best strategy to store those in Elasticsearch?
So you define actually analyzers per field. So my previous answer still applies. You can just choose that on a per document basis and even per field basis. So you can actually configure it as you wish. And you always have the option of just giving up and analyze everything as every language and just basically create a matrix that you can then search across the whole thing. Because searching across multiple fields is not that much more expensive. So you can afford to search over many fields or over many versions of the same field. Okay?
So a little while ago I accidentally built a geocoder, and those street names are very weird. So I did a lot of the things you suggest, like standardizing all the text and stuff. But one of my challenges still is that we have a lot of long names where the user might be typing halfway. So instead of searching for Django, they're searching for Ango or Django. Is that handled also in some way by the methods you described?
Yes, so there's not in what I described so far, but it's handled. There are many ways to handle it. The first one is you can do a fuzzy search that will basically search like the neighborhood of the term. Again, using an edit distance as a guide. Or what you can do is you can build an n-gram. You can use an n-gram analyzer, and that will basically take all the parts of the word. Let's say you define an n-gram of length 3, so it will actually index all the triplet letters in that name, and then it will do match on that. So if you have Django, it will index Jag, Jan, Eng, and so on and so forth. So then someone searching for, in this way will actually get the results. Thanks.
When it comes to searching, the bit of the element in the room is your online search interface, which is haystack. And I was surprised in your slide you, I suppose, in purpose avoid it. And, you can tell a few words about why.
Okay. Yes. So haystack is what I described as the generic search interface, because it's fairly limited in what it can do. It was also custom built for Solword. So it can do some of the things that Solword can, but even not all of them. And it definitely doesn't translate well to all the other search engines. And that's why I was emphasizing that this is actually all the boilerplate that you need. This is what Haystack provides you, plus some nice API to actually build the queries, which is something that I'm working on to reproduce for Elasticsearch specifically, but also something I believe that you should own, because that's where the magic happens. That's where you can add value to your users, and you should actually, in my opinion, invest a little bit into learning how you can query the data store that you choose and use it. So it's more about the difference between the ORM and have ORM with specific features for Postgres, as we've already heard here. Like, you can get more of your data store if you actually know what, if you target it specifically, instead of just throwing things out there and seeing what sticks. Okay, any other questions? So we have a few more minutes. So I can actually go over the things that didn't fit. So the first one that I want to talk about a little bit is autocomplete, because a lot of people use n-grams for autocomplete and do actually search for autocomplete, which is not an ideal approach for several reasons. Search is slow, and by slow I mean a couple milliseconds or 10 milliseconds or something like that. Add to it the return trip, and it's already too slow for you to be able to run it on every keystroke, which is typically something that you want for autocomplete. So you should have something specific in place. Also, if you're auto-completing on something that starts with like 2 letters, relevancy has absolutely no meaning. The standard relevancy, how we actually calculate it during the search phase. Because what's more relevant to your two-letter query? Who can tell? Nobody knows. So instead, what I would recommend is use a dedicated autocomplete suggester. So, for example, in Elasticsearch, there's a completion suggester. It's based on a very, very nice data structure called an FSD, which is a finite state reducer. It's basically a finite state machine. So any auto-completion is just one pass through this data structure. So it's very, very efficient. By very efficient, I mean sub-millisecond response times. And the score and the text on which you should autocomplete is provided by you. Because there is just no other way how we can autocomplete on 1 letter or 2 letters. We need you to supply us all the possible values that you want to autocomplete and their score. Their score in this occasion is fixed. So typically what you would do is you would have the score, for example, if you're searching for repositories on GitHub, you would have the score based on their popularity, given the assumption that typically you want to autocomplete something that's popular. Or if you're searching for a hotel, again by popularity, or by closeness, or something like that. So something that stems from the business logic, not from the data, because we don't have enough data to make an educated guess. So that's my rant on autocomplete. Like, speed and relevancy just exclude search, and you should actually use a dedicated service for it. So another thing that people often do is they try to sort their results. They basically ignore the relevancy, and instead they sort on something like the date of creation, or alphabetically, or something like that. And while that works, and all the data sources can do that, it's typically not something that you want, because then you're throwing out the window all the advantages that using a data source like that gives you. So what you can do instead, if you actually want to take the freshness of the project in place, is use a custom score thing, which actually lets you influence how the score is computed. For example, you can say that certain documents are more important based on their popularity, or based on their closeness to the user's location, or based on anything else. You can even just plug in your own little script, your own little formula, how to compute the score. So let's say you'll take the original score, you divide it by 2, you multiply it by 3, and then you add the third digit of pi. And of course you can do that. That's not very rational to do. But for example, you can add the staleness of the project, you can add popularity, you can multiply it by the number of users who search for the same thing, etc., etc. There's a lot you can do. So you will get the documents that are really good, but not that good a match, but they're really, really good. And also you will get the documents that are not that good, but are a perfect match for the query. And you will not get rid of either of those results, which scoring would do. With sorting, it's either by score, so you get the relevant, or by popularity, so you don't get the most relevant one because it's not popular. Okay, so I'm out of time, so if you have any more questions, come find me, I'll be happy to answer them. And otherwise, thank you for listening and having me here.